In this video, I am going to show you how to analyze and find unknown values in a series circuit. We should probably start by asking, what is a series circuit? One definition of a series circuit is, a series circuit is one in which the resistors are arranged one after the other, and the electrical current has only one path to follow. So, let's take a look at what that means. So here is an example of a series circuit. A battery supplies the potential voltage to cause an electrical current. The current runs through each resistor one after the other. Another type of circuit is a parallel circuit. We will be looking at these in more detail later on, but it can be instructive to have a look at one for comparison to a series circuit. Like the series circuit, the battery still exists for a source of potential to cause a current. However, when the current gets to the junction of wires at the top of the circuit, it will split into two, and the current through resistor 1 will be different than the current through resistor 2. The current will come back together at the junction at the bottom of the circuit and then pass again through the battery. Now let's start to analyze this series circuit. These can be a lot of fun to analyze because it's essentially a puzzle based on a couple of rules like Ohm's law and Kirchoff's laws. Our goal here is to find the currents I1, I2, and I3 for each resistor, and also the current through the battery, and then also the voltages V1, V2, and V3 for each resistor. In other series circuit analyses, it may be necessary to find the value for a resistance, given other information about the resistor, such as the current, or the voltage across resistors or the battery. Another concept that we use to determine the values in a circuit is that of an equivalent resistance. So let's ask the question now, what is the equivalent resistance of this circuit? That is, if we were to replace the three resistors in the circuit with one resistor and cause the same current, what would be its value? We will start with the fact that current in this circuit is the same at all points, at the battery, at R1, R2, and R3. This is because there's only one pathway on which the current can travel. If the current was greater in one part of the circuit compared to another, then the electrons would pile up on each other, and they can't do that because they repel each other. The next step is to use Kirchoff's voltage law to state that the amount of voltage gained by the current passing through the battery is equivalent to the sum of the voltage drops across the resistors. Recall that moving through voltages is like going up and down. So this means that if you go up 6 volts, you have to come down a total of 6 volts in a closed loop of a circuit. What goes up must come down. Next, we're going to apply Ohm's law. Ohm's law is electricity equation number 5 on page 4 of the reference tables, and it says that resistance is equal to the voltage divided by the current. This can be arranged as voltage being equal to resistance multiplied by current. Okay? We can use this fact to rewrite the Kirchoff's law equation in terms of resistances and currents. The voltage through the battery will be the current through the battery multiplied by the equivalent resistance. Remember that this is the resistance of the circuit if the 3 resistors were replaced by a single resistor to cause the same current. Ohm's law can also be applied to each individual resistor, and so each resistor voltage drop can be written as the product of the current through that resistor and the resistor value. Now, at the beginning of this, we wrote that the current through the battery, I, is the same as the current through each of the resistors, I1, I2, and I3. Because of this, we can cancel out all the currents in the equation because they are like terms. This results in the equivalent resistance as being equal to the sum of the component resistors. So we simply add them together to get the total of 12 ohms for the equivalent resistance. The next step in our analysis is to determine the current I through the battery. We can find this by the application of Ohm's law. We know that the voltage given by the problem is 6 volts. We have also calculated that the equivalent resistance is 12 ohms, so we can simply substitute these values into the equation. Solving for I, we find it to be 0.5 amps. Next, we'll find the currents through the resistors, I1, I2, and I3. Recall that the current in the series circuit must be the same at all points along the circuit. So, since we have already calculated the current through the battery, we already know the currents through the resistors. It's simply a matter of entering their values. Finally, the only thing left to find are the voltages across each resistor. Because we know the current for each resistor as well as the voltage drop, it's simply a matter of applying Ohm's law for each resistor. This means that V1 is 2.5 volts. V2 is 1.5 volts. And V3 is 2 volts. You can verify Kirchoff's voltage law and see that the sum of the voltages across the resistors is 6 volts, which is the same as the voltage of the battery. We have now completed the analysis of this series circuit. The rules that govern series circuits that we have used in this analysis can be found on page 4 of the reference tables under the title Series Circuit, also shown right here. There will be more examples forthcoming to solve, some in different ways than this one, based on the knowns given in the problem. The end.